Okay, let's start. Good evening, class. Can you hear me and see the share screen?
Yes, sir.
Yes, teacher, yes.
All right,
Yes,
all
lecturer.
right, all right. Thank you. All right, thank you, everyone. Class, today we're going to finish the remaining part of the simple linear regressions. But before we move on, let me briefly review what we discussed last week. Class, last week we discussed simple regression model. Why do we need the simple regression model? So with simple regression model, you can estimate the effect of X on Y. With correlation, you cannot clearly identify which variable is independent, which variable is dependent. With simple regression model, you can clearly identify which variable is dependent and which variable is independent. So remember, you have your research question and objective. So basically, you want to assess the relationship between X and Y, or you want to assess the effect of X on Y. How much Y change if X is increased by 1 unit. With simple regression model, there are only two variables. Both variables must be numerical or continuous. All right. So with simple regression model, you write like this. You have y equal delta 0 plus delta 1x plus u. Y is dependent variable or explained variable or response variable. X is the independent variable. X independent from Y, but Y depends on X. Or you can also call X as explanatory variable or regressor. Delta 1 is your main interest. In order to assess X on Y, you need to compute delta 1. And that delta 1 is called slope parameter. At the same time, you can also generate delta 0, which is called intercept. But for now, you only focus on delta 1. So all the variables that you include in the model, in X, you call independent variable. But at the same time, there are other variables that affect X that you cannot include it in your model. They are all in error term or disturbance or specifically unobserved variable. As you see the term itself, unobserved. You cannot observe it because you do not include it in the model. All right. We then discussed that normally to interpret the simple linear regression, you look at the change of Y given the change of X. So again, your interest is delta 1. And normally Y error term is assumed to be 0 because with the change of error term given the change of X, there is no X with error term, so it could be 0. All right, so I give you an example of a few examples of the relationship between fertilizer and yield, education, and wage. All right, so with simple regression model, there are multiple ways to compute delta 0 and delta 1. But the way that you try to construct delta 1 and delta 0 by minimizing the sum of square residual, it's called OLS. All right, OLS. So with OLS, you minimize residual sum of square residual in order to find delta 1 and delta 0. All right, and even though you don't have to compute yourself, but at least you need to know where this delta 1 come from, where is delta 0 come from. So you have to take a good note of this mathematical equations. All right. We then try to interpret delta ones given the example of the return on equity and CEO salary, and also the rate equation and education. We then discuss the goodness of it, or specifically R square. Remember that. All right. So R square equal 1 minus SSR, which is sum of square residual divided by sum of square total. So again, R square measure fractions of total variations that explained by regression. In other words, it explains how much the dependent variable is explained by your model, the model that you only include only one independent variable or only one exponent. All right. We then talk a little. I give you an example by interpreting delta 1 again and R square. That was the end of last week lecture on simple regression. And today we're going to move on. But before we move on, are there any questions from last week lecture? So the key point is you need to know the equation of delta 1, specifically how to interpret delta 1. You need to know the equation of R square and how to interpret R square from last week. All right. But you also need to know that in order to compute delta 1 and delta 0, when you minimize the sum of square residual, that method is called OLS. Any questions before we move on?
Hello, teacher.
Yep.
Teacher, I'm having a question. Can you explain a little bit about how to minimize the sum of squared regression?
All right. Basically, I do not explain it in here, but you can further review the textbook. They are a little bit complicated for those who are not interested, who do not have a strong background in math. So normally with this, okay, minimize residual sum of square here, you have this equation as the residual, then you square it, and then you minimize it. So normally when you minimize residual sum of square, you try to make the residual sum of square equal 0. And then there are some assumptions that you need to do in order to get delta 1 and delta 0. But there are some steps which you can consult with the textbook in more detail, and I did not explain it here. Why? Because as I said, I want you guys to focus more on applied methodology rather than theoretical. But it is important. If you can consult with the textbook, and if you have questions, you can contact me. Is that okay? The textbook have do that in detail. So the way they minimize sum of square residual, basically, they try to how do we say, to calculate or to find delta 1 and delta 0 by assuming that the by equalize square residual, sum of square residual equals 0, and then you can solve the equations. But there are some assumptions like as you have first order conditions and so on. When you look at the textbook, you will see that in detail. Is that okay? So I do not explain in detail here. Any other questions, or you want to ask a follow-up questions? All right. So I basically pick up only the main points where you guys do not need a complicated math to understand it. All right? Is that okay? What's that, David? Something wrong with from the side of it. So to answer the question in short is that we minimize sum of square jewel by equalize the equations equal 0, and then we try to solve the equation. Then we assume that we come with 0 conditional, mean we come with expected u equal 0. I don't go into detail that because many of you here will find it complicated. All right. Then let me move on to, let me continue our lectures on the simple regression model. So now you guys know that in order to find delta 0 and delta 1, so basically we want delta 1, let's say delta 1, okay? Because that is the slope of parameter that tells you the relationship between x and y. And in order to find that, you need to minimize sum of square residual. But in the process of minimizing sum of square residual, there are some assumptions. And today we are going to discuss the assumptions. All right. So for econometrics, if you remember, you need economic model, and then you need econometric model. And with that econometric model, we have to understand the assumption. How do we minimize that sum of square residual? But at least you need to understand the assumption. So now, last week we only concerned about the relationship between x and y in absolute term or in non-log. But with simple linear regression, when both variables are numerical, we can also transform either your dependent variable or independent variable into natural logarithms. All right. There are some reason behind this. Why do we need to transform into log? But for now, you don't have to know this. But if you read some paper and you see that some paper using log, for instance, rather than using weight, the paper using log weight, for instance, there are some reason behind it. For instance, one of the reasons is that they want to have a normal distribution with this variable. All right. So as I said, for now, you don't have to understand the why do we need log, but at least you need to know how to interpret it. All right. So now, for instance, you want to assess the relationship between education and wage, but at this time, the author, the researcher, do not use absolute value of wage, but rather they use log wage. All right. You all know log, right? Natural logarithm. So how do we interpret this then? So when we have dependent variable in natural logarithms, the interpretations in simple is like this. All right. You look at the end, but here the change of log in weight divided by the change of education, and then you can solve this equation. So at the end, we have the change in weight divided by weight by the change on education. So the interpretation is, if year of education increased by 1 year, the wage will be changed in percentage, not in each unit, right? Last week, and there is no log, 1 year of education increase is associated with how much of this delta in wage in unit of wage. But now because of log, our interpretation is in percentage. Let's have a look at the example. All right. So for instance, here we try to assess the relationship between education, and now our dependent variable is log wage. So now we have delta 1 equals 0.0083. The interpretation is the wage increased by 8.3%. So you have to multiply this delta 1 by 100, right? You have to multiply by 100. So you get 8.3%. So wage increased by 8.3% for every additional year of education. In other words, if education increased by 1 year, the wage increased by 8.3%. Remember, this is different from last week. When both wage and education are no log or in absolute value, we simply say 1 year increase in education increase wage by blah 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 dollar per hour. But now because it is in log, 1 year increase in education increase wage by 8.3%. Okay, how we calculate this? You can see this our equation earlier. All right. Can you follow me? And normally the relationship between education and wage, normally it is not log, it is in straight line. But now it is in log, it is not in straight line, it's a little bit in the curve. So it observes non-linearity. But for now, if you don't understand it, don't worry. But what I want you to know is how to interpret it. Any questions? With the relationship of education and log wage. All right. So let me move to the next slide. What if both variables are in log? All right. Now assuming that both variables are in log. So again, we want to assess the relationship between sale and salary of CEO. But now because of data, because of some functional form, because of the literature tell us that there is not linear relationship between blah, blah, blah. Then we need to transform both salary and wage and sale into natural logarithm. So in this case, if you look at here, our equation, the interpretation in both sides will be in percentage. All right. If sale increased by 1%, there will be change in salary by percent. So both of the interpretation must be in percent. Here is an example. So here is the result on the relationship between log salary and log sales. So how do we interpret is this? If sale increased by 1%, the salary of the CEO increased by 0.25%. So in this time, because both sides are log, we do not multiply by 100, right? We do not multiply by 100. So simply look at the delta 1 and explicitly interpret it as percent. So it is different from the earlier case. Questions? Can you follow me? Question everyone? All right. Let me move next.
Teacher.
So again, yep.
Teacher, can you re-explain that a little bit?
All right, here. This is the delta 1 of the relationship between sales and salary. So because both variables are in log, you can say simply as if sale increased by 1%, because it's in log, let's say this is because it's in log, we can translate why this equation here. It tells us that both variables are interpreted in percent. If you want to know the result, or if you don't, if you found this is complicated, you can just remember the rule. All right. So if sales increased by 1%, the salary of CEO increased by 0.257%. That when both variables are in natural logarithm.
Teacher.
Yep.
Okay, right.
I cannot hear you properly. Some reflections.
We can also write log as ln, right?
Can you write in the chat box? Can you write in the chat box? You can drop your question in the chat box.
Teacher.
Yep.
So usually log we have the number below. Is it log 5 or log 4 or something, teacher?
This one normally when normally when you write in log, that is log with base 10.
Oh, what about the log len, the len?
Len that is an exponential 2 point something, but normally
okay.
it doesn't matter. It doesn't matter whatever log base you use, either lens or log 10, log 20. As long as you use both are the same, then the interpretation is still the same. All right. So as I said, there are some reason behind it why we need to transform your variable into natural logarithm. One is because of data, they want data to be a little bit normal distribution. Because weight, for instance, if you ask everyone weight, the data, your data on weight might not be like this, but it might be, for instance, like this. All right. So when you use logarithm, the data becomes smaller, so it gets closer to normal distribution. But another reason is that when you use log, actually I told you before that you don't have to understand the reason, but since you ask. But the other reason is that when you use log, it can tell you that your regression line is not linear, but your regression line is seems to be a curve. All right. That is why we say that this is incorporate nonlinearity, semi-logarithm form, something like that. All right. So there are some reasons, but how do you know that? For now, you just need to understand how to interpret it. But for your research, when you conduct more literature, you will know that, you will see that some paper use logarithm, and then you see the justification in that paper clearly. All right. Do I answer your question? Yes, we can also write in length. All right, David. So as long as if you use both length, both are in length. All right, with log here, normally when you write log, this is log base 10. You remember? All right. So you can use with log 20, log base 20, or whatsoever you like, but make sure that both at the same time it follow the same rule. If it is length. So next, after this log, when it comes to hand-on exercise with data, I will teach you how to transform the data to logarithm. But we don't use log, we use len. Len is better, is quicker. All right. But again, the same rule, as long as you use the same base form, log base 10, and len is commonly used. But again, even though you use len, but normally in writing form, they suggest you to write in log. I rarely see any written form as len. All right. It's better to use log salary form, and so forth and so on. Is that clear, everyone? Davin, and I cannot see your name clearly, so my apology. I love to call your name, but I cannot see your full name here. All right, Odom. All right, is that clear, Dom?
Yeah, clear, sir.
All right, good, everyone. So for now, as I said, you just need to remember of the rule of interpretation. If you look at the textbook, you can see the clear rule. So I suggest you guys not just simply come here without prior reading. If you have a prior reading, it would be great. So if you have some question, then you can clarify with me. All right. So now let's go next. So far you already know that the OLS with the minimized sum of square residual allow us to find delta 1. And that tells us that the estimate regression coefficient are come from random variable that we calculated from random sample. If you look at this equation, basically, when we want to estimate delta 1 hat, what is delta 1 hat? Is that slope of parameter or slope estimate? So don't forget the term. When it comes from the sample, we always call it estimate. When it comes from population, we call it parameter. All right. So delta 1 hat here is the slope estimate, or sometimes I simply call it estimate. So if you look at this equation, so we calculate this delta 1 hat simply from data that is random and depends on particular sample that we have been drawn. We did discuss about sample with the statistic review. All right. So here, if you look, we have, as long as we find value x and y, and then you can calculate x bar and y bar, then you can, of course, calculate delta 1 hat and delta 0. But the question is, what estimator will estimate a rate and how large the variability in the repeated sample? What if we collect sample several times, like what we did with the statistic review? What happened? So we need to understand the expected of delta 0, expected of delta 1, and variant of delta 0 and variant of delta 1. So to understand this, we need to understand the assumptions that we use to minimize sum of square residue. So even though you don't understand the math behind it, but you just need to know the assumption. I will try to simplify the assumption. So first, there are 4 standard assumptions for linear regression sample. So SLR here, class, as you can see, the SLR here, it stands for simple linear regression. So S for sample, L for linear, and R for regression. All right. So the first assumption is that in order to use simple linear regression, in order to use OLS, in short, because here we refer to OLS. So here, in order to use OLS, the relationship between x and y must be linear. Must be linear. When we say linear here, we refer to this delta 1. Delta 1 must be linear. So that delta 1 cannot be delta 1 square or delta 1's power 3, no. Or log delta 1, no. That delta 1 is simply a delta 1. When we write it as delta 1, it tells us that it is linear. So make sure that this delta 1 is not square or root square whatsoever. All right. So in order to use OLS, the assumption number 1 is that x and y has linear relationship. So most of the time, you don't have to concern with assumption number 1. So assumption number 1 is okay. All right. But I just want you to understand what do we mean by linear in parameter. So that delta 1 is simply delta 1, not square, not log, not exponential. All right. That's assumption number 1 to use OLS. Assumption number 2. Give me a minute. I got a cold. I'm not quite sure if this is COVID-19 again. All right. All right. Now, assumption number 2. Your data must come from random sampling. And we already discussed this with the statistic review. When we say random sampling, it must come from probability or random sampling method. All right. It is important because we want to make sure that the respondent number 1 and respondent number 2 has nothing to do with each other. That's why X and Y are not correlated. X1 and X2 has nothing to do with each other. So the data is a random sample drawn from population. For instance, what if you use quota sampling method? You know what I mean by quota? Or what if you use, what do we call snowball sampling? Snowball sampling, when you interview the first respondent and then you ask the first respondent to identify the second respondent. So there may be the case that both respondents has a relationship. In that case, X of the first respondent and X of the second respondent may be correlated. So make sure that you use random sampling. All right, so X data point therefore follow population equation. Everyone have equal chance. If you use snowball sampling or convenient sampling, not everyone has equal chance. Otherwise, your data do not represent the population. And normally, if you use the data with the quantitative data, that is not your main concern. All right, so make sure you use random sampling, probability sampling. All right, so this is the first two assumptions. The first two assumptions is not a main concept. All right, but remember, if you collect data, don't say I use non-probability or non-random sampling. Make sure you use random sampling. If you use non-random sampling, you cannot make inference, you cannot make conclusions for the population. Okay, for the population. An equation with assumption number 1 and assumption number 2. So in order to use OLS, make I will conclude what do we mean. So in order to use OLS, it is best if both X and Y, the relationship is linear. The data you obtain from the respondent must come from random sampling. All right, this is the first two assumptions. All right, next, if it is come from the random sampling, you can see this line here. It represents the simple linear regression using the OLS. All right, and this is the error term. You already know what is error term. Error term is the the actual Y minus the delta 0 minus delta 1 minus x1. So it depends on the random sample. Sometimes it is bigger than the expected Y on the line. Sometimes it is lower than the expected Y from the line. Now, next, assumption number 3, sample variations in explanatory variable. What do we mean? We mean that the value of explanatory variable X not all the same. Here, it's very connected to random sampling. If, for instance, you do not use random sampling, it might be the case that X of the first respondent and X of the second respondent might be the same. What if you interview the household member in the same household? All right, so they're gonna have the same X. So the assumption number 3 is very simple. Make sure that if it is come from random sampling, all the respondent will provide you with different value of X. All right, that is why it is mathematically it is written as summation of I equal 1 X bar x1 minus X bar square must be higher than 0. And again, if you do random sampling, this assumption number 3 is not your concern as well. Understand assumption number 3? So with regression class, normally assumption 1 to assumption 3 is not your concern. It's not your concern. All right? But your concern is assumption number 4. Assumption number 4, last week we start by calling it as, I forgot it, the conditional mean assumption, something like that. But now assumption number 4, in simple, we call zero conditional mean. And most of the case, assumption number 4 is the main concern in any study in econometric analysis. All right? In econometric analysis, assumption number 4 is your main concern. In the next 2 weeks, we will discuss multiple linear regression, and then you will learn more about zero conditional mean. So what do we mean by zero conditional mean? Zero conditional mean tells us that the expected value of error term given X equals 0, which means that the value of explanatory variable must contain no information of mean of unobserved variable. What do we mean? Similar to last week, we mean that the variable that affect Y, the variable that affect Y and also affect X must not be inherited, or all the variables that affect both your x of interest and y must be included in your model. That's what it means. And again, the assumption number 4, zero conditional, means it depends on your literature review. It depends on your reading. You will, when you do some reading, and when you want to estimate the relationship of x on y, your research objective, the price on quantity of demanded, when you do reading, you know what are the factors, what are the relevant variables that affect both of your x and y and must be included in the model. If you do not include in the model, assumption number 4, zero conditional, mean is violated. All right, hopefully you guys understand what we mean by assumption number 4. If you don't, again, next week when we discuss about multiple linear regression, you will learn more. All right, so when assumption 1 and assumption number 4 are met or not violated, so basically number 1 to number 3 is okay, but number 4 is really a major concern. If number 1 to number 4 are met, the expected beta 0 and beta 1 are expected to be the same as beta 0. In other words, we say the slope of parameter that we estimate from sample equal slope of parameter. I made you the wrong word. I say this again. Slope of estimate from the sample will equal slope of parameter from population. All right. If assumption number 1 to assumption number 4 are met. Class, here, if your regression, if you do the regression analysis and all assumption number 4 are met, that is best. That is best. In the econometric topic, we always try our best to address assumption number 4. Always try our way to address assumption number 4. Of course, there are some other problems that you will learn next, but for now and in the future, we always keep, connecting to this assumption number 4. But if assumption number 1 to 4 are met, not violated, it can be said that your beta 1 is unbiased. Okay, your beta 1 is unbiased. What economists really want is that we want unbiased estimate. If your beta 1 is unbiased, you can make causal interpretation. If your beta 1 is biased, you cannot make causal interpretation. In other words, if assumption number 1 to assumption number 4 are met, all right, you have unbiased estimate, you can make causal interpretation. You can make causal interpretation. All right? Follow me? And that OLS produce unbiased estimate, or we call unbiasedness of OLS. Follow me? Any questions up to now? All right. No questions? If there's no questions, let's move next. All right. What about variance of OLS estimate? So far, we only discuss about the estimate, but we do not discuss about variance of estimate. What is the variance of estimate? The variance of estimate when what happens when you have a multiple sample and each sample produce each estimate, and if you calculate that estimate and then you will have variance of estimate. What happened to variance of estimate? So variant of OLS estimate or variant of this delta 0 or delta 1 class, it depends on sample. Estimate will be nearer or farther away from true population value. It depends on your sample. All right. So how far can we expect our estimate to be away from true population value? It depends on sampling variability. What is sampling variability? It is measured by estimator variant. So now we need to estimate variant of delta 0 and delta 1. Don't worry. I will give you a key message that's very simple. But to understand, to learn about variant of estimate, we need additional assumption. And that assumption is called assumption number 5, is homoscedasticity. All right, it is written as variant of error term given x equal delta square. So what it means? It means that the value of explanatory variable must contain no information about variability of an observed factor. In other words, the variant of error term must not depend on x. What do we mean? What do I mean is that here, if you look at this mathematical equation, variant of u given x equals delta square. There is no x with here. So meaning that it is not conditional on x. Make sure that the variance of delta or error term is not conditional on x. So what we get here is like this. All right. We get that the variability or the residual is constant. You look at the graph, it constant when x increases. That is an example of homoscedasticity. Don't worry, this is your first time. We will have a separate lecture on homoscedasticity. All right. So assumption number 5, we want homoscedasticity. We want variance to be constant. If this assumption 5 homoscedasticity is violated, the graph look like this. The graph look like this. You see, now if you look at the variant graph, it is not constant. When x increases, the variance is also increases. All right. When x is small, the variance get closer to mean. But when x is increasing, the variance get farther and farther from the mean. So the variance of unobserved determinant of weight increase with level of education, meaning that those who have higher level of education have higher variance. That's what it means that our residual is not constant. Our variance is not constant. If it is not constant, if the assumption number 5 is violated, we call it heteroscedasticity. Heteroscedasticity. All right. So what do we mean? What we mean is that we want to estimate variant delta 1 and delta 0. So finally, the equation of variant of delta 1 and delta 0 is written like this. So if you look at delta 1, it's just the variant divided by the total sum of square. And you know that total sum of square when we discuss about goodness of fit. All right. Here, now with variant delta 1 and delta 0, of course you can estimate error of variant, but I don't want to confuse you. So let me skip this. But from this variant, from this equation here, the variant here, if you remember from statistic review, we can calculate standard error. All right. So now we calculate standard error of delta 1, standard error of delta 0 from the equation that we have earlier. But because this delta here is the population variant, and we cannot have population variant, we can use the sample variant instead. So we use delta hat square rather than delta square. All right. And here to calculate this, we just square root of variant. All right. And what we mean is that if assumption 1 to assumption 5, so earlier we only discussed about assumption 1 to 4. If assumption 1 to assumption 4 is met, we obtain unbiased delta 1. But, sorry, not but. If assumption number 1 to 5, not 4, if assumption 1 to 5, we get unbiased standard error. In 2 weeks time, you will learn why do we need unbiased standard error, why do we need unbiased beta 1. Because we will need to do some hypothesis testing. We need to generate T star 6 P value. All right. But now you need to know that from assumption number 1 to 4, OLS produce unbiased estimate. OLS produce unbiased beta 1. However, in addition, if assumption number 1, 2, assumption number 5 are met, OLS produce unbiased standard error or unbiasedness of error variant. All right? Questions? Brain is burning. That is the end of today's live. Question everyone. How are you? All right. So class. All right. For today's lecture, the key point is you need to understand how to interpret nonlinearity when we discuss about log. And next, you need to understand what X assumption means. Assumption number 1, what does it mean? Assumption number 2, what does it mean? Assumption number 3, what does it mean? And assumption number 4, what does it mean? Assumption number 5, what does it mean? And then if assumption 1 to 4 are met, then you learn that OLS produce unbiased estimate, produce unbiased beta 1. If assumption 1 to 5 are met, OLS produce unbiasedness of error variant or standard error. All right, that is the summary of what we discussed so far. Questions? All right. If there is no questions, we still have about 20 minutes before break. Now let me move to the hand-on exercise of using Stata. And now let's move quick to how we analyze regressions in Stata. How do we calculate fitted or predicted value, residual, and how to do log, transform log, and so on. Right. So now one last time. Any other question before I move to Stata? No. All right. All right. I assume there is a no. Wait a minute. So class, it's time for Stata now. Can you confirm? Can you see the share screen?
Yes, teacher. Yes, we can see it.
All right. All right. Everyone, please open your status. And class, in the folder, you should see file name Vig file. So there are two new files, Vig file simple regression and Vig file simple linear regression. There is a hand-on exercise like this with some explanations. Can you find it? In the folder, make sure you access to the file. All right. It provides you the detail how we do a simple linear regression, how you generate fitted value or predicted value, how you generate residual. All right. Class, before we move on to Stata, allow me to quickly introduce you guys to and Stata webbook. If you are keen to learn more about Stata and econometrics, you can click the link in this reference. It will connect you to the Stata webbook that developed by a number of authors, published by UCLA. So here you see the Stata webbook. So starting from simple and multiple regressions and so on, step by step first. All right. So if you keen to learn more about Stata and econometrics, you can use the link in the reference to learn more by yourself. All right. Just in case you want to learn more. All right. For now, make sure you open this file and Stata. Class, can you find the file? It is in our folder, the general file and lecture note. This two new file, and this the last one here is what we need for Stata hand-on exercise. Before we move on, just want to make sure that everyone have access to the file on your PC, and you open the Stata now.
Wait, teacher, I'm still downloading.
Right. Ready, everyone?
I'm ready now. Like,
Can you show the location again, Sir? I just got disconnected here.
All right. The file here is in general channel, and then you go to file, and then you go to lecture note. This one.
Okay, sir. I saw it, sir.
All right. Can we move on? Can I start now?
Yes, sir.
yes, sir, yes.
All right. All right. All right, class. Now, as usual, you go to your data, and then you need to open your last do file. All right. Make sure you use only one do file. It's better so that you can have a look and edit it later. So now I need to open my last do file right here. All right. But for now, I am going to have a new note in which I want to discuss about simple linear regression. All right. Simple linear regression. All right. So today we discuss simple linear regression. Let's say here we have week 5, simple linear regression. All right. Now let's get back to the documents. All right. So before we proceed to simple linear regression analysis, you guys need to understand the context. You need to understand the objective. Okay. But here is just an example. All right. So let me read the file a little bit. So let's begin by showing some example of linear regression using data. In this type of regression, we have only one predictor. What is predictor, class? What is predictor? Predictor is X or Y. We have only one predictor variable. Ask yourself, do you remember what do we mean by predictor? Predictor is an X. All right. This variable may be continuous, but for now we only use continuous, meaning that it may assume all variables within the range. For example, age or age, or maybe the short autonomous. It's okay. But now this variable is continuous. All right. There is only one response or dependent variable, and it is also continuous. As I said, for simple linear regression now, of course, it can be any variable, but for the starting point, you guys need both variables are continuous. All right. So now with this example, we want to estimate the relationship between enrollment and academic performance. Class, before we proceed, let me ask you a question. All right, not yet. Okay. In Stata, the dependent variable is listed immediately after regress. All right. Command followed by one or more predictor. So this is, it tells us how to do it. So normally, if you come back to Stata, it tells us that you start with regress, and then you type dependent variable. What is your dependent variable? And then followed by independent variable. Now, let's examine the relationship between size of school, right? Examine the relationship between size of school and academic performance to see if size of school is related to academic performance. Now, the research question and objective for this example is the relationship between size of school and academic performance. Before we proceed to the analysis, class, you need to have your own prediction. In simple, you need to have your own assumption. Do you expect to see positive relationship or negative relationship between school size and academic performance? What is your assumption? In other words, it can be your hypothesis, technically. What is your hypothesis? Do you expect to see positive relation between academic performance and school size or negative? Any idea? Just your assumptions. It can be right, it can be wrong. Nothing. Sorry, it is not right or wrong, but you want to test. You want to test, right? This hypothesis can be based on your sample in some place. For instance, if you collect data in some provinces, you may expect that there is negative, but in some provinces you expect maybe positive. But in general, for the sample, we do not know where the sample is from. But what do you expect to see? Do you assume that there will be a negative or positive relationship between academic performance and school size?
Negative relationship, teacher.
Negative. All right. So class, always it is very important to ask yourself, to make your own prediction, assumption. If the result is different from your prediction or hypothesis, you need to ask yourself why. All right. Is it something wrong with our econometric model? Or is it something wrong with, or there is nothing wrong, but it's probably because of the context. All right. We now discuss about econometric. When we see something unusual, we need to ask, is there something wrong with econometric model? For instance, now, as Davin said, we expect to see negative relationship between academic performance and school size. What if we found positive? Is that make sense? If it does not make sense, is that probably because of the context? If that because of the context, you need to find the reason to explain it. If it is not about the context, you need to ask yourself, is my econometric model is correct or not? All right, let's move on. Now let's assume that our assumption or hypothesis is that there is a negative relationship between the academic performance and school size. And you remember, for some of you who studied with me before, that hypothesis is called hypothesis of associations. All right. So now, before we do this, we need to extract data. Okay. For this data, for this example, we use, for this example in here, FP00 is the dependent variable and enroll is the predictor. So now, class, you need to load in the data from the internet. Copy this, put in your do file. All right. Probably you can write clear first in order to clear any existing data in your Stata. All right. Where is my Stata? Here's my data. So far there is no any variable, but I just write clear first, run do, and then I copy the data. All right, and then run do. And now the data is loading in my Stata. Make sure we are all the same page before we proceed to the next step. Guys, any problems with loading the data?
No, sir, but can you tell the full meaning of API 00?
Oh, that is the variable. Let's load the data first.
Load
So,
already.
all right. In here, they tell us that the academic performance variable is named AP00 in their data. Okay, AP00 here is just the variable name for academic performance. Is that clear? And the variable name for school size is enroll. See that? So AP00 is just a variable name. You can name it any variable name that you like. Okay, do I answer your questions?
Yes, sir, yes, sir.
All right. Everyone, does anyone have any difficulties or problem with loading data from the internet?
Teacher, I cannot load the data. It appear the red line.
The red line, what does what the red line state?
It says something about the certification, wallet certification.
Did
Enable
you
to find wallet certification part to requested target.
did you simply copy use and then blah blah like mine, like this? Make sure that only use here, only use nothing between before use, and then you follow, you exactly copy and paste. If you can't tell me, I will share the data with you now.
It still cannot show. Maybe my
right.
version is correct.
Wait a minute. Then let me save the data and share it with you guys. Wait a minute, class. So self, I name it as simple regressions. Right. Let's say this is big file. Big file simple regression .dt .dta. So if you want to save your data, comma replace. All right. I save the data. All right, now the data itself I will share with everyone in the chart. All right, you can see my share screen right now. So the teaching material, sorry, it's data, big file, simple regression. All right, now I share with you, please just download and then you can click open the file. All right, probably we need to move our hand-on exercise after break. For those who cannot load data from the internet, please load the data that I share with you guys in the chat box. Can you see that? After you click on it, make sure you save it as in your directory. Or the best way for you guys just to double click on the data, then it will load into this data automatically. All right, it's already time. So now let's have 30-minute break as usual. Then we will start our hand-on exercise after break. Class, again and again before break, make sure the data is loading in your data. All right, so after break, we can continue to hand-on exercise with data. All right, I see you after break. Our 30-minute break start now. Please return to the room at 7:15 or 16. See you after break. Hello, class. Are you back in the room?
Yes, sure, I'm here.
All right, all right. Let's continue. So before break, we discussed the objective of this exercise, that we want to estimate or assess the relationship between the academic performance and school size. So we expect that it's gonna have a negative relationship between the two variables. So to run the regressions, simple regression in Stata, you can type regress, right? Then dependent variable. What is our dependent variable? If you remember, FP00. What is our independent variable? We have enroll. All right. So this is regress and enroll. Then you should obtain this result. Did you get the result? Can you get the result? Any problems? Sorry. So this is the result. Could you get it?
Yes, sir.
All right. But normally, class, it's better before you run regression analysis, it's better to run some descriptive statistics. And you remember, for numerical we run, we do summarize. What's that? Summarize. All right. Then we can summarize the two variables and we run regressions. Right here, we got this. This is the summary. You see that the academic performance, there are 400 observations. The average academic performance score is 647. The minimum is 369 and the maximum is 940. And the school size is enrolled also 400. Min is 483. Minimum is 130 and maximum is 1,570. And this is our regression. So what you learn from simple linear regression, you learn about R square, and you learn about delta 1, which is this. This is delta 0 and standard error. All right. So we only need to interpret what we just learned from linear regression. So what it tells us here, class, we can go back to the material, to the documents, then look at the result. Now, let's review this output a bit more carefully. Now you see there are some interpretation on the other result that you do not study yet, but you can skip it. For instance, now they explain F test, but for now just skip it first. All right. R square. So as you can see, R square of 0, 10, 12 mean that approximately 10% of variance of academic performance is accounted for by model. In this case, in this model, there is only school size. That's how we technically interpret R sphere. Can you see the highlight? Can you follow the interpretations? All right. So R sphere is 0, 10, 12. So basically it means approximately 10% of the variance of academic performance, which is AP00, is accounted by the model. And our model only have school side. All right. That R square. For now, you do not have to interpret the t-test. All right. You just need to look at the coefficient. All right. The coefficient, it is here. Let me highlight it. So the coefficient of enroll is minus 1989,674, or approximately almost minus 0.2, meaning that for 1 unit increase in school size, or in this way, in this variable we have enroll. So 1 unit increase in schools in enroll would expect a 0.2 unit decrease in academic performance. So this is how you interpret delta 1. All right. Can you follow the interpretation of both R square and delta 1, everyone? Of course, there are other results, as I said, as statistics, T statistics, which you will learn in 2 weeks' time. Any questions? With the coefficient delta 1 with minus 0.99 blah blah here, we can say, in other words, a school with 1,100 students would expect to have an academic performance score 20 units lower than school with 100. So this is just a calculation. You don't have to interpret that if it is not convenient for you for now. All right. So this is what it really means for delta 0 and delta 1. Are you following me, everyone? Any questions? Can you follow the interpretations? R square and delta 0. Now, if we connect this to the assumption class, assumption 1 to 4 tell us that this regression produce unbiased coefficient if assumption 1 to 4 are met. If assumption 1 to 5 are met, the standard error here is unbiased. All right. So standard assumption 1 to 4, if they are met, we have unbiased coefficient. If standard assumption 1 to 5 are met, we have unbiased standard error. And this both coefficient and standard error will be used to generate T statistic, which is the hypothesis testing which we will discuss in 2 weeks' time. All right. So for now, you just need to know that this coefficient need to rely on assumption 1 to 4. The standard error need to rely on assumption 1 to 5. Follow me? Questions? Any question, everyone? Problem with running your regressions or interpretation or getting that fund result? Let me know. All right. Next. Okay. Questions? By the way, here you have problem with loading data from internet. Can you use the data that I share with you?
Yeah, teacher, I already saved your file and it's work now.
All right, good. Any question, class, before we move on? Make sure you understand this. If you could not understand this, when it moves to multiple regression, it's gonna be difficult for you. If you understand this, multiple regression is not that hard for you. All right. Now let's move on. Let's continue. If you look at this one, it also tells you how to generate the fitted or predicted value. All right. So now let me just continue reading to give you guys some idea. So in addition to getting regression table that we just produced, it can be useful to see scatter plot of predicted and outcome variable with regression line plotted. So after you run regression, you can create variable that contain predicted value that using predicted command. So what we are going to do now after running regression, we can generate fitted or predicted Y. Remember that? What is fitted and predicted Y? Y that is generated from regression model. So you can get this value at any point after you run regression. So after you run regression, you can generate fitted or predicted Y. So for this example, our new variable name will be FV. FV, all right? FV represents fitted value. So in this case, it's simple. If you want to generate fitted or predicted value, just write, okay, after here, you just write predict. FV here is your variable, new variable name. You can have any variable name you like. For instance, I can have it as fitted API. Any variable name you like, all right? So to make it easy and so that everyone can follow, just have fitted FV, all right? Then you run predict, and then Stata tell me that the name is already constructed. Oh, because I ran it 2 times, all right? So I only run it to see here. If you look at my data, I already have FT here. Follow me? Now, if you want to have a better look, you can, order both original Y, which is FP00 and FV. Then you can look at the data to see the difference. All right. So if after I order it, the data is in order. This is original Y. This is predicted Y. And then you can compare. This is based on this is original data. This is the predicted Y from equation model, which we calculate from Y equal beta 0 plus beta 1 plus X. Are you following me? Questions? Here, when I order it, I order FP and FV so that I can easily compare the original Y and the predicted Y. Okay? Can you follow me? Any questions? Or I am alone?
No question, teacher.
All right, can you follow me? You can follow me, right? All right. In other words, if you don't want to order, you can simply list. All right. You can list FP00 and FV. In here, list FP in, but it say here in 1 to 10. This is the first 10 respondents. It means the first 10 respondents, and you can see it here in your data. Here plot, it tells you. You list FP and FV in the first 10 respondents. Then you can also look at the difference. Instead of order and then look at the original data. All right. So next, what we are going to do is to plot to generate a scatter plot between our dependent and independent variable. So here we normally have y dependent variable on vertical axis. So y first, followed by x. So you can have scatter plot. Okay, should be like this. This is your data, your original data. All right. Any problem with getting the data? Now, I do not want to confuse you many other graphs, but what I am going to do next is to generate residue. All right, to generate residue. You know what is fitted y, you know what is residue. All right. So here to generate residue, you can simply run predicted E, and then residue. All right. So here predicted command followed by variable name. In this case, we use E as the variable name. And residual option tells us that we want residual. Okay, so you can say, for instance, predict E residual. How do I spell this? I'm wrong. Let me try it. Options residual. I wrote it incorrectly. Oh, I forgot A. All right. So predict E residual. Right. So now I have the data. Now I have residual as well. E is residual. Can you follow me? You can also generate residual by simply call generate E. For instance, now I can add another residual. Okay, E1 equal FP00 minus fitted value, right? It should be the same. Generate. You see, E1 when I use predict command, E when I use predicted command, E1 when I manually calculate it. Can you follow me, class? Either you use predict E residual, or here I just because E already in our database, I cannot use E again, so I have another variable named E1. So here I just use Y minus fitted value. I also get residual. Can you follow me? Can you follow me with regression analysis, with generating the fitted value, and now generating residual?
Yeah, could you explain E1 again, please?
Pardon, I cannot hear you clearly.
What is E1 again? Could you just now?
Here. E or E1 here is just the name. All right, it's just the name. So our goal here is to generate residual. Instead, when you write predict, E is a variable name. Here you want to generate residual. So what name do you want? So in this, if we follow this file, they name residual as E. But the residual option here, it is a must. You have to write residual, meaning you want to predict residual by give it name as E. All right. But this is when you use predict. But predict here only work when you run regression. All right. Only when you run regression. If you don't run regression, predict E does not work. But since I already have fitted Y or fitted value, I can generate residual using original Y minus fitted value. But here I give it the name as E1. E1 here meaning residual as well, but this residual I generate from y minus fitted y. Is that clear? Do I answer your questions? So E and EY just the name for residue. Is that okay, David?
Yes, teacher.
Question, everyone? Any questions? Can everyone follow me? Can everyone follow me? Here I can give this note as generate, fitted, or predicted y. Any questions? Can you follow me? Are there any problem with running your regressions, generating your predicted or fitted y, and generating your residue? If you look at data, either you use predicted option or to manually calculate it, the result is the same. Question, everyone? Is that okay, class? If you have any problems, don't be silent. Let me know.
Hello, John.
Yep.
So actually, regarding the data and the loading, I don't have any problem with data, but it is really difficult for me to understand the shortcut of the data that show, for example.
Oh,
like,
okay. Correct. I understand what you mean here. This is the so normally there is an what? There is a data description, but with this example, because I go through with you, so I will explain you one by one. But if you want to understand the detail of this data, you can go to this web book, the reference that I show you, and then you follow them, and then they will explain that data. All right. So the data that they use, they will explain you one by one, but not in detail. It's only example by example. So your concern is how do you understand this variable name? What does that really mean? Correctly here?
Yeah, teacher. And one more thing regarding the regression. Can you go back to the table of regression?
All right. This one.
Those words like coefficient, standard error, and t. Sometimes I can't remember it all. Like what does it mean in full word? Like the t and e as something.
Here, as I said earlier, what you have to need to know for today is these are where you learn, right? Coefficients. Here you can look at the detail in our example handout. That's why I submit this, and you have to take note. You have to take note yourself with this document, with this file. All right, it tells you this is the coefficient. All right, and this is standard error. We will discuss T or P value we will discuss in the next week. But for now, you just need to know this is R-square, how to interpret it, coefficient, how to interpret it, take a look, and standard error. You just quick look at our lecture note. We have the full written text. All right. Is that clear for you? Do I answer your question and your concern?
Yeah, teacher, yes.
So you have to take note yourself. All right. A simple answer is you have to take note yourself. And that all of this result, as I said, connected to what we discussed in simple linear regression. And the term are used there, used in there. And also the handout that I share with you also provides some information and the writings there. Any other questions? So class, again, it is important that you guys have to review what we studied. If you don't review, you cannot follow me. If you cannot review or just try to understand and take note the key message that I tell you at the end of each lecture, or from the beginning of each week, I always try to summarize the main point. All right. So if there is no other question, let me move on to hand-on exercise. And I will tell you how to run regression with, remember we discussed about natural logarithm. Now, our original regression is the relationship between enroll and academic performance. Both variables are non-log. All right, and non-log. What if, assuming we want dependent variable in log, what should we do? So first, we have to transform our academic performance, transform variable to log, into log first. So in this case, generate, all right? How do you understand this command? One by one, learn with me, and don't forget to remember to review the stata exercise, that's the stata slide that I share with you. And this command, you will remember it if you frequently practice it. Because I do it every day, that's why I remember some of them, not all, but I always refer to the document as well. So now we want to transform FP00 to log, all right? So to generate first, I generate, then I give it a name as log, all right? Underscore FP00. And what I'm going to do is, in stata, we use length, all right? And then FP00. Now we have a new variable name called log FP00. All right? Follow me. Then I click do. My new variable is successfully generated. Follow me. Follow me. We transform your variable from non-log to log. And as I said, it is as long as you use the same base. But here we only use len, but I write it in log. You can write as len as well. It's up to you, right? Either if you use log, make sure you always use the same name. All right. From now, I can run a new regression. Rather than use FP00, I use log FP00 and then enroll. All right. Now we get different result. Earlier, our delta 1 is minus 199, but now our delta 1 is 00134. Because when we use different measurements, we have different interpretations. We discussed that earlier. What is the interpretation here, class? If enrollment increased by 1 unit, what happened to academic performance? Our delta 1 now still negative, but the magnitude, the number, the figure is different. Earlier interpretation is if school size increased by 1 unit, academic performance changed by or reduced by almost 0.2 units. But here, what happens? What is your interpretation? Get back to the slide, to the handout, to the lecture note. What is the interpretation? By the way, did you guys obtain the same result as mine? Can you transform your dependent variable from non-log to log right now? So what I am trying to do here is to connect what we just studied from the theory to the application. Questions? Can you follow me? How do we interpret how do we interpret our result right now? Questions? Can you follow me, class? Are you on the same page with me? How are you now? Yep. Is everything all right? All right. So our interpretation is, if you look at the lecture note, if enrollment or enrollment here stand for class size is increased by 1 unit, the academic performance is decreased by, we take this delta 0 multiplied by 100, and then we get the academic performance will be decreased by 0.35%. That is an interpretation. If enrollment increased by 1 unit, the academic performance will decrease by 0.035%. Okay, that is the first one. Now, what if we want to use both dependent and independent variable in natural logarithm? So now we also need to transform our dependent variable, independent variable. So now I use a new name named log and enroll. All right. So it equals length enroll, and then I click do. So our variable is created, no error. Then I type a new regress. I use most variable in natural logarithm, fp00, and then log enroll. Now I run regressions, and I see that we have a different coefficients, but the sign is still negative. The sign is still negative, right? Follow me. Can you transform your variable from non-log to natural logarithms? And then, did you obtain the same result as mine? Any problems, challenge, questions? I am very worried because you don't reply me and I don't know what's going on. This week, the first quiz will be released. The first quiz is very easy. Make sure you get a good score. Class, did you obtain the result last month? How should we interpret our result? Have a look at the lecture note. How do we interpret this regression result when both independent and dependent variable are in natural logarithm? So any problems, questions? All right. Since there's no reply, assuming that everything is okay. So based on our lecture note, the interpretation is if enrollment or class size increased by 1%, the academic performance decreased by 0.15%, right? No multiply 100. If enrollment or class size increased by 1%, the academic performance decreased by 0.15%. Technically, some interpretation states when enrollment increased by 1%, academic performance is associated with minus 0.15% change. So this is just a different way of wording. The meaning is still the same. Question, everyone? Can you follow me with the hand-on exercise, with the applications and interpretations?
Yeah,
Yes.
so
Yep.
when both are logs, we don't multiply them by 100.
Can you type your question in the chat box? Navin, drop your question in the chat box. Reflections. Any other question, everyone? I'm still waiting for. When both variables are locked, we don't multiply. Yes. Sorry, no, we don't. You can refer back to the lecture note. Also, class, if you have a look at the handout, there is a clear rule there for interpretation. All right. So now let me show you. It's better everyone to don't forget to do some reading. Don't too much rely on the lecture note. Okay, lecture note is just some sort of summary. So if you wait a minute, I tell you where is the interpretation rule. Up, 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 up. No, wait a minute. Where is it? Here it is. Do you see the share screen, everyone? Here it is. If both y and x are what we call level, change in y is simply the delta 1. But if y level and then x log, the delta have to be divided by 100. Okay, so this is the rule. You can refer to the textbook or the lecture note, but the textbook is more detailed. Okay, but the answer is no. Don't multiply by 100. This is log. All right. So percent change in x, delta 1 is percent change in y. If y is log, x is non-log, change in y multiply 100, percentage change in y. All right. Is that clear, David? Any other question, everyone? For the remaining time after this applications, I'm going to ask you guys to work in group. Because it is too much now in the brain. Any other question before I ask you guys to assign you guys to work in group? No? Do we have a quiz today? Not today, this week. Normally, the quiz is designed in a way that it allows you to consult with lecture note and reading material. So the quiz that I designed is to force you guys to read, to review the material. So I give you Friday for a quiz. Okay, so to have a good score, you need to read. If you look at the answer, you look at the question, and then you can answer. You have Friday to do your quiz. All right. So I'm not here to kill you, but to force you to read, to understand, to learn. All right. I assume there is no question about these data applications. And today's lecture on simple regressions. Am I correct, everyone? Can I move on to explain what I am going to ask you guys to do next? All right, class. For the last 30 minutes, it is your own options, but I would request you guys to work in group, to discuss in your group. Now, what I am going to ask you guys to do is work in your group and identify a paper. Of course, you have already, your group have already identified a paper, but I want to make sure that you guys identify a paper that use regression analysis to answer your research questions. All right. Again, for the last 30 minutes, discuss with your group member, identify a paper that closest to your research question and objective, but the paper must employ regression analysis. After you identify that paper, upload the paper in the assignment folder week 15. Is that clear? You have to submit the paper by the end of today's lecture. Oh, it's maybe, sorry, it's too, probably you made it time. So let's say you have to submit the paper just after you identify the paper that close to your research objective, and that paper employ regressions, then upload the paper in assignment folder and week 5. So here you have to submit it here. All right, let me show you like as usual. Internet a little bit slow. So now, assignments. And now week 5. All right. So upload your paper here. Upload your identified paper here. Before next Tuesday, 5 p.m. I will not put it in announcement, but remember yourself. Is that clear, everyone? It is a group. Make sure that I can see a clear file name with your group ID, with your group name. All right. Make sure I can see a clear file name. Is that clear for everyone? You have 30 minutes for your discussion. And I am going to stop here. You can discuss whatever platform you have. But next week, we will have another discussion in my own platform. But for today, you can have a separate discussion with your own group. Sorry, be honest, I am a little bit uneasy because I got a cold. Is that clear for everyone? Question about the homework?
No, teacher.
All right. If that is all, allow me to stop here. But the remaining 30 minutes is a Zoom. It's supposed to be your group discussion time. Make sure you have an identified paper that use regressions to answer the question and put it in the assignment week 5 folder. That is all for today, class. I'll see you next week. All right.
Goodbye, teacher.
So enjoy your discussion. Enjoy your discussion. Not the end of the class, but you do your own discussion. Right. Okay.
Lecturer, so we have to submit it at 8:30?
Before 5 p.m. next Tuesday. Probably during the discussion, someone may have some idea that it may ask every one of you to identify separate paper and then to come to discuss again.
Okay.
So
Lecturer.
before next Tuesday, 5 p.m. Okay. Originally, I thought it's better to request you guys to submit before 8:30, but some of you may want to get some more time, want to have some more time. Thank you, Kim Hua. All right, everyone, have a good group discussion. Don't forget the deadline. I see you next week. Bye-bye.
Bye, lecturer.